Hi guys, it's Mr. Y. Today we're going to be talking about measurements and some graphing. It's important to remember that with any type of graphing and measurements, we always want to use the metric system when available. Having a different set of units is a lot of times confusing. Most of the world uses the metric system, so in most cases, unless you're really expecting to have a narrow audience that you know is going to be typically American, most scientists will use the metric system. Otherwise, you get different standards of units like you see in this little cartoon here, and it doesn't make for very easy understanding of what's actually happening. So we're going to be talking about how to make the perfect data table. That is a data table that will be graded and receive 100% of all the different things that have to be included. Same thing with the line graph, because those tend to be the most common types of graphs you'll have to make for a science class. Everything that you need to have a perfect line graph. And then talking about how to measure units like length, weight, volume appropriately, and hitting on terms like mass, displacement, and meniscus. Now, perfect data tables have lots of different components. First of all, they have to have a title that's appropriate. So you can see the title on this graph down here. It's average rainfall in Santa Fe. Labels for every set of variables. Our labels in this case are time and rainfall. And then within each of those labels, there should be units of some form. The units for time is months. Again, units are usually in parentheses. That's why I have put them in parentheses up here. The units for rainfall is inches in this data table, and all the categories must be filled in as much as possible. That is to say, nothing is left blank. If there's a value that comes to 0, you better have a 0 in there. Keep in mind, some of these values are actually pretty close to 0, but they went so far as to be specific as to down to into the tenths place of the decimal system. So if you have no data, you should either be putting not applicable or you should be putting a zero value. Let's look at another example. This is a much more detailed data table. Again, has titles, has labels for every set of variables. Notice the labels this time is time and location. The units, again, months, and then you have the months down here. And then the units for location is in actually cities, and then you have the different cities right here. And again, everything is filled in as much as possible. When there is no data available, you put a 0 value. You do not leave it blank. Moving on to graphs. Again, you must have a title, must be appropriate to the graph itself. The axes of your graphs, whether you're doing a bar graph or line graph, must be labeled, and they must be scaled properly and equally, meaning your highest value should not be more than 2 times your highest point. In other words, my highest value here is at 20. I should not see this thing scaled up to 40. There's no point in doing that. I stopped my scale at 25, which is a nice way to stretch out the graph to make everything filled in properly. Also notice my scale is nice and even. It goes by 5, so 0, 5, 10, 15, 20, 25. And then here the months are all evenly spaced out. There's no difference, between this space over here and this space over here. It's exactly the same every time. Notice also that the data points are perfectly lined up with my notches. So here lines up with here, lines up with here, lines up with here. This should be all one perfectly even system, so that the space between any 2 data points is always the same no matter which line you're talking about. So evenly spaced there. Now, oftentimes with line graphs, you'll also have to have a key system. Talk about that, which is over here on the left, so that you can see which line represents which variable, which unit of the variables. Making sure, of course, that all your data points are lined up and correct is your responsibility. That's usually where students tend to lose the most points, making sure you have a key. And also, guys, keep in mind, sometimes line graphs don't always work. Sometimes a pie graph works better when you're talking about composition, or a bar graph when you have a lot less data to deal with and you want to just see a simple comparison. So let's look at a bar graph next. Again, bar graphs must have titles. The axes, again, label with units, label units, which is actually here, 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 and here. And notice again, spacing is perfectly even. It's the same distance from here to here as it is from here to here. Everything's nice and evenly spaced out. Again, I have a nice scale of 5, 10, 15, 20, 25. Again, your scale is going to depend on what your highest value is. In this case, it's about 24, I'd figure. So you don't want to put your scale for this kind of graph up to 50 because that would be a pointless waste of space. So pick your scales appropriately, responsibly. Make sure you can show as much in your graph as possible. Don't waste space. Pie graphs are when you want to show compositions of a whole. So again, all these percentages, 4%, 4%, 7%, all these little percentages here have to add up to 100%. If they don't, something's off. Again, pie graphs, if you have lots of variables, you're going to want to use a key system. And again, title, oftentimes, because pie graphs don't have axes, we'll put the units in the title. So the units are actually here in the title. So the units month. So graphs can always be a great resource for visualizing the results that you get out of any experiment. So it's a great way to actually help prove your point. Not, I shouldn't say prove, to support your point. Don't use the word prove when you're trying to show a relationship. And while graphs are always a good thing to know how to master, you must first, of course, master the idea of measurements, how to actually get the data for your graphs. So obviously with length, we're measuring distance between two different points. The standard units is meters, kilometers, or centimeters. There are other units in the metric system for distance or length. The good thing about the metric system is it's always based on 10. So everything is a division of 10 below it or a multiplication of 10 above it. So you just go 10 times 10 and you're at the next unit up. Mass is another unit we talk about. That's the measure of the amount of matter in an object. And conversely, you have this other system we use a lot of times called weight. And a lot of times in science, especially in biology, we'll use the term mass and weight interchangeably. In physics, it becomes more of an issue, but you have to know that there is a slight difference because weight is not just the mass of the object, it's the mass of the object multiplied, you can see this in the formula here, by the acceleration of gravity, which is roughly 9.8 meters per second squared at sea level. So these two are not the same thing. They use the same units though, so it tends to confuse students. Don't let that throw you. For our purposes in biology, they are the same, but if we're talking physics or chemistry, a lot of times they are not the same. And the best way to convey this is it's with this little picture here. You can see this little gentleman. He weighs, we're going to use this pounds for this because that's what this is cartoon to scale for. He weighs 100 pounds on Earth and only 16.6 pounds on the moon. Now, does he have the same mass in both places? Does he have the same amount of stuff, the amount of matter in both places? The answer is yes, he has the same mass, but his weight is now different. Why is his weight different? Because gravity on the moon is much, much, much less than 9.8 meters per second squared. And because this value dropped and this value remained the same, the overall outcome, so you multiply them together, drops as well. Let's talk about volume. Volume is how much space an object takes up in 3 dimensions, length, width, and depth. The units for volume are the same as you would see for the units for liquids because liquids are best measured in units of volume because they don't have regular shapes. So when you're on 2 dimensions, a solid object that doesn't move all that much, the equations for volume don't really apply. Volume only applies when you're talking 3 dimensions, so down here. And you can see that with these geometric shapes, the equations don't look nearly as easy as they do when the objects are in 2 dimensions, when you're looking for area. So a lot of times in science, you either have a choice. You can either work with really hard math equations, You can find a way around them. The way around volume is this little concept called displacement. That is measuring the volume by putting a sinking object, must be something that sinks, into a known amount of water. It's best when you're talking about some object that's not a perfect cube or not a perfect cone or a perfect sphere. So you take this irregularly shaped object, this rock here, you dump it in some known amount of water. At this point the water is up at 7. After it sinks, the water rises to 9, i.e. the water has risen 2 units. That is the volume of your irregularly shaped object. And again, this can be weird if the object is too big, so you got to make sure your container is big enough as well. Now, in science class, you have to be aware if you do this process with graduated cylinders, there's this little effect called the meniscus curve. A meniscus is a Greek word meaning crescent, and it's a natural curvature in the surface of the water thanks to water's ability to adhere to itself along the edges. And so when you're looking at a graduated cylinder like the one on the right in the yellow, you have to make sure when you're reading the line, you're reading it at the correct volume, where this is your eye line here. They don't really show the eyeball. This is the correct way. This is good. These two are bad. If you're too high, you're going to get a low reading. If you're too low, you're going to get a high reading. So you got to make sure you're nice and even with the actual lines of the meniscus curve, so you read from the bottom of the curve, right here, not at the top, here. And don't be too high and don't be too low. Here's a real picture of a meniscus curve. Again, you will want to say that the value here is about 6.6 if you're looking at this straight on. Again, you're reading from the bottom right here. So 6.6. So I'm going to give you guys 2 sets of data tables that I'd like you to do graphs for. Make sure you practice making your titles, your labels, units, variables, everything perfect. Make sure you're doing it on graph paper and using straight edges, using rulers preferably. So go ahead and copy this down. You can pause the video here. Time, remember, almost always goes on the x-axis. You see I have a title here already. You can borrow that title. I have labels with units. Everything's filled in. You have to decide on the scale. You're going to be making a line graph. Here's your second data table. Again, you're making a line graph. I have titles you can borrow, but this time there's going to be 1, 2, 3 different lines. So again, you make sure you choose the appropriate scale. Start with your highest value. So remember to find the highest value before you start, and then you can show me the graphs when you come to class.